10,000 by 10,000. Right. I hope that is good. I need to change this. Fuck, how do I change this? Channel, this, channel, reader dashboard, stream manager. Not doing Doom. Learning all of physics forevermore. I will explain everything. Misanthropish. The profit of Misanthropish has come out of hiding. Boom. Art. Learning. Arts. Physics. Physics. Learning. Drawing. Drawing. English, select content. Category. Okay, category arts. Which Twitch. Browse. Just chatting. League of Legends. Software and game development. Sports. IRL. Music. Art. Art. Art is. Art. Done. Okay. Well, we can start and I can lay the foundations of what I'll be doing today and over the course of, well, my entire life. You see? Let me just put everything in its place. This is in its place. This is in its place. Let me just check the comments if I can, maybe get a comment or two. Activity feed. My chat is here, right? And if I can move this here and this here and this here, that should be it. Now I can say something like welcome and here welcome and check on my phone. You can tell me if everything is right. Let me see. Let me go to the YouTube first. YouTube first. YouTube. The stream is starting. This is just my first stream of this caliber, so I will need to you know calibrate everything. And calibration is the mother of all evil. Let me see. Is the voice? Yeah, the voice is fine. Misundersh, welcome. Okay, that's perfect. Not that perfect. Why is it auto? Higher picture quality, please. Advanced. Can we get a higher picture quality? We can. It works. Alright. On the YouTube side, it works. We are late, 17 minutes late. But that's gonna be our first piece, art piece. Every day, we're doing a few things. And I will explain those things just after I go to Twitch and see if the comments and everything works there as well. Twitch. Twitchy. We'll be starting at 8:20. Let's be honest. 8:20. Twitch. Not Twitch. Mizun Trash. Trash. Go to Mizun Trashy. And it's live. Come on, I have one more minute and then I'm starting. Okay. Okay. My internet is terrible now. Right. Okay. You can go here to Twitch. All categories Twitch. Who's streaming? I'm streaming. Channel. Let's see. I'm offline. Why am I offline? Can it start? This is stream preview. Right. Bitrate is okay. Chat is okay. But it's preview. Home. You're live. Manage stream. Stream preview. Offline. Can it possibly get better? Twitch. Okay, it's live. It's live. I am streaming in art and there is nothing to be streamed here. Is it streaming at all? Stop streaming, auto stop. On YouTube it works. On YouTube it works, I can see it working. On Twitch it does not work. Due to probably a big bitrate. Okay, why is it offline? Unstable. Maybe I should fuck with the settings a bit. Okay. Settings. Main canvas. Advanced settings. Default. Twitch output. Save output. Advanced settings. Main encoder. NVIDIA. Okay. Maybe now it works. Come on. Come on, you can do it. Offline. Somehow. Main canvas. Right. Main canvas. Vertical canvas. Main canvas. Add an output. Okay. Come on, Twitch. Oh, is it working? Ignore the chirping, is it working? Ignore the chirping, is it working? It's working, good. Good, I can follow it here, and I can put my YouTube chat here. This here, everything is perfect. We can start. So the plan is every single day until the rest of my life, I shall forevermore be the jailer of physics. And that would mean I would draw for 1 hour. Now it's only 35 minutes, one art piece. After drawing the art piece, I go and I study physics, like in detail, like from mechanics up to quantum mechanics, electromagnetism, everything there is to know, scientific papers, everything. I want to know every single detail of existence. So this is what I'm gonna do. This will make me act a certain way where I cannot just skip an example. I need to really do it and finish it, and so and so and so and so. First, we're gonna, you know, draw a friendly, a friendly, uh, a friendly thing, and let's go. I'm gonna choose some very fine lines, and I'm gonna draw. And this is gonna be the boring part. But after the boring part comes the less boring part. As you can see, this is gonna be some freaky shit. I don't know what it's gonna be, frankly. But what's gonna happen is I'm gonna draw now for 35 minutes or so, and then speed physics for 4 hours. This is gonna be the first episode. So in the first episode, we will do very little of actual physics. We will try doing some, but we will watch videos from other creators. We will do stuff. Now I'm just doodling, and doodling is important to get your mind in the creative mood which is required for physics. Um, After a while, I would like to pass all my exams by doing this method, and I would like to, you know, not fail, become the greatest physicist that ever was. That's a tall order. Egotistical much? Fuck yeah. Okay, so I know nobody's gonna watch for many, many, many days. But this drawing session is to get me in the right sort of head for doing physics. Now I'm thinking, and I'm thinking about the problems of physics, the string theories, how it's unfalsifiable, uh, and so and so. The Unruh radiation and Hawking radiation, which somehow merge concepts which we know nothing about, which is also inspiring. The three generations or so of particles, which does pose the question, really, on all of us. And so on. We will watch videos, but we will start with mechanics. And I have done mechanics, I have passed mechanics. Do I remember enough mechanics to just speed roll through this shit? I don't know. Probably not. Some of those are pretty hard for an untrained eye. And I am definitely of the untrained. 4 hours every single day. This is how I start my journey. So we'll be here. If you have something to say, you can always say it, and I will read your comments. And after I read them, I might respond. You can ask me questions about physics, and I will answer them to the best of my ability, which is not a lot of ability. I have spent all my life learning physics and realized I know nothing. I know absolutely nothing. So if I know nothing, then it's time to learn something, isn't it? And boy, is the time, has the time come. What is this supposed to represent? I don't know. But we are gonna add some color red. Red eyes. Red me waves. Woody daddy. Where did they was? Where did daddy? Where did they was? Where me daddy, where me daddy, where me daddy, where was? And then the nightmares came to the fluster of the great God in beyond. Where is Misanthresh? That's a good question. Here is Misanthresh. This is Misanthresh, my god. Born on the 5th of December 2018. I'm just gonna write that down. 5th. 5th of December 2018. Great. We need thicker lines. And by thick lines, I really do mean thicker lines. Okay. The eyes speak sweet justice that make men shiver in the dark. I make YouTube videos. I haven't made one since well, I guess summer, and I intend to keep making them. I have some videos on Zoth, and Zoth is gonna be an interesting video. But yeah, physics. What else is there to it? I hope this unknown can be used eventually to help people, because this will be a hard task. A very hard task, which I'm currently not avoiding but preparing myself for. Alright. New color, purple. Purple is for the eyelids. And purple how much time? 8:34. I have it even there. 8:34. 8:34 and we are on to war. We have this. I'm gonna represent it there. Good. Good. Now what is this? I don't know. But it represents my tackling of physics. And by the end of the year, I will have over 300 paintings. And all of them representing how I feel in the certain moment. Alright, time to give it some form. Some form. So, no, this is the wrong color. Blue is the color I want. And the blue, 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 and the blue. Ba da boop, boo da da boop, ba da boop, boo da da. The smiles grow deeper this time. And the eyes grow darker. Red again, but let's do it a bit pinker. And this time it's a bit more avant-garde. Beautiful, beautiful. And the eye, teal. Teal eye. With a very dark pupil. And some veins. Okay. Now we go to the oranges. And the oranges, they represent, well, something, I don't know what. Sorrow. Oh, what were we on the time? 20 more minutes. That is beautiful. Beautiful. We return to the blue ones. The blue ones. They go. The blue ones. They grow. The blue ones. They off. And I am here entertaining the lot. So please entertain. Ah, yes. And fingers. They are where they are. This crispy ass. Okay, and we open it up. Mm-hmm. This is beautiful. Beautiful. Mm-hmm. Okay, new color. Green. Green as for the corruption within. And then we go to black. $2.45. $2.45. Will I be able to actually finish this piece by 2:45? I don't know. Pretty good thus far. Mhm. Now it's time for thicker lines. Great. Thank you. We have here a thicker line. Great. Oh, right. Oh, the cameras. Oh, can it? Interesting. So the camera does like blushing. All right, we're better, faster, stronger. Doombo, doombo. Okay. Okay. We continue the drawing. We have 5 more minutes until we start doing physics. Okay. Now, of course, we are back to 10 lines. A 7 would do. And here. In 5 minutes we will have our jobs back. Okay. Now it looks a bit better. Beautiful. And we have this. Beautiful. pink for the last. A bit of a color to it. A bit of a, tone. So it sees it's made of flesh, not just alien parts. Alien parts. Okay. All right. Nine oh one. I will extend it a bit, just so we're clear, until I finish the piece, because I think it's a bit beautiful. And orange. Be a bit more orange here. Differentiate the parts perfectly. Okay. I think we're done. File, save, save as. Day one. Okay, I can close. Good. Beautiful, 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 beautiful. Bitrate is stable. YouTube is stable. Let's go. Okay. How do I know I'm ovulating? Okay. How do I write notes on my laptop? Let's see. God.
Methods my a picture.
No, I want to write them. I want to write them. For drawing notes in class. Scribble ink. Journal by Microsoft. Inkto. Scrivano. Microsoft Journal. Why not? Continue. Next. Next. Okay. Okay. Go back. Select with the tab. New journal. Physics. Day 1. Color red. Okay. Can I just, tap to the page? Boom. Okay. That works. No. Uh, Settings. Display and appearance. Dark mode. Page position. Okay. About. No. Okay. How do I make it bigger? enter language, delete page, insert page above. Okay. Okay, got it. Got it. So we have physics. To learn all of physics, one must understand where physics originates. We must understand the birth of the scientific method, sci-fi method. We must understand many things. Among them, Newton. So now we're gonna go here and we're gonna go a guide to a good theoretical physicist. How to become a good theoretical physicist. Okay, classical mechanics is where we will start. Okay, an intermediate level course on classical mechanics. Okay, we are starting from here. Introduction. Intended audience. Okay. Next. Newtonian dynamics. Okay. Okay. Next. Modes of motion. Okay. So, we have this guy Newton. And he thinks about stuff. Thinks about matter. This is an object. And it says to us, oh, it says to us, this is gonna go here, and this is gonna go here. Okay. And this is gonna expand to fit there. Okay. So, in his work, which we have Philosophia Naturalis Principia Mathematica, he discusses in 1687. Okay, we go next. We have three laws. Law number one. These are postulates. These postulates are the groundwork for the theory. And we will mention when it doesn't fit. Okay. So everybody will move with a v. No matter anything, v being velocity, measured in meters per second. That could be 0, that could be pi, that could be 137, which is a number too associated with stuff. To change the motion, i.e. momentum, of an object is proportional to the force impressed upon it, and it is made in the direction of the straight line in which the force is pressed. So if this object moves like this with a v, and we want it to move like this with some other v, we must exert a force here. That's second law. Okay? And the third law is that if we have a ball hitting a ball, they will hit, and the force of the collision, the force exerted, the force impacted, will impact the most beautiful of them all as well. So the balls will just bounce right off, assuming, you know, uh, elastic collisions, not plastic ones. Okay, let's go next. Okay, here we get to the good stuff. Just up here. Boop. Newton's first law of motion essentially states that that a point object subject to zero net external force moves in a straight line with a constant speed, i.e. does not accelerate. So acceleration is zero. However, this is the only true in special frames of reference called inertial frames, which is any frame where you have, to my knowledge, where you have inertial frames are basically frames where you do not have an acceleration or a shifting of the space. Yeah. Okay. Acceleral moves in a straight line with constant speed. Suppose that we have found an inertial frame of reference. Let us set up a Cartesian coordinate system in that frame. The motion of the point object can now be specified by giving its position vector r, x, y, and z with respect to the origin of the coordinate system. So this is the origin of the coordinate system. This is the origin of the coordinate system. This is our point. This is r is this with respect to the origin of the coordinate system. Got it? Okay. With respect to the origin of the coordinate system as a function of time. So if we use time here, t, that means velocity. Consider a second frame of reference moving with some constant velocity u with respect to the first frame. So we have first frame where things are not moving, and we have a second frame where the things are moving, if I'm understanding it correctly, like, I don't know, v. With respect to the first frame. Without loss of generality, we suppose that the Cartesian axes in the second frame are parallel to the corresponding axis in the first frame, so that u 0, 0, 0. Okay. And finally, that the origins of the two frames instantaneously coincide at t equals 0. So t0, the origins of the two are coinciding. Suppose that the vector of our point object r, new vector r dot, in the second frame of reference it is evident from the figure that at any given time t, the coordinates of the object in the two frames satisfy x, the new x, is equal to the old x minus ut, or vt, I guess, as we called it. Okay? And the others don't change because we said that they don't change. The others are the same. Okay, this coordinate transformation was first discovered by Galileo Galilei. So I will say Galileo. Is it with two L's? No, Galileo Galilei, and knows and is known as the Galilean transformation in his honor. Good. By definition, the instantaneous velocity of the object in our first reference frame is given by v is equal to the derivative of r with respect to time, which means derivative of x with respect to time, derivative of y with respect to time, derivative of z with respect to time. Okay? How do I scroll without doing this? I don't know. Okay. With the analogous expression for the velocity v prime. In the second frame, it follows from the equations of 1 to 3, which are what? Yeah, 1, 2, 3. Okay. That v of x nu is equal to v of x minus u, and the same for the others. These equations can be written more succinctly to mean v new is equal to v old minus u. Finally, by the definition of the instantaneous acceleration of the object in our first reference frame is given by a, which is the derivative of velocity with respect to time. So literally, we're looking at curves here. If we have for v, if we have this as position and this is time, and it's moving like this is our velocity v. And if we have of v with respect to time, this is our a. If it's like this, it clearly does not change given time, so a is 0. If it's like this, the v does not change with respect to time, it's 0. And we can write this as dv dt of x dv dt dv z dt. Okay. Okay. Acceleration in the second frame, it follows from differential equations 4 to 6 with respect to time, in that the acceleration components of the two frames satisfy, well, they satisfy that. They just are. Or the new acceleration is equal to the old acceleration. Okay. If an object is moving in a straight line with constant speed in our inertial frame of reference, if i.e. if a equals 0, then it also moves in a different straight line with a different constant speed in the second frame reference a what equals 0. Hence we conclude that the second frame of reference is also an inertial frame. Okay. A simple extension of the above argument allows us to conclude that there are by infinite number of inertial frames moving at constant velocities with respect to one another. Newton through that one of the Newton drew that one of the Newton through that one of these inertial frames was special and was defined as an absolute standard, i.e. rest. A static object in this frame was the state of absolute rest. However, Einstein showed that this is not the case. So this is literally Einstein versus Newton. Newton says, okay, there is absolute rest, so we can do math based on the absolute rest. And Einstein says no, but we'll get Einstein in a later, much later episode. Hmm. 1 second. 1 second. Okay. All right. Okay. Where was I? Oh yeah. And that's relativity of the frame. Consequently, one inertial frame is just as good as any other frame as far as Newtonian dynamics is concerned. But what happens if the second frame of reference accelerates with respect to the first? In this case, it's not hard to see that the equation generalizes to a equals a minus du dt. Okay. Where du or u is the instantaneous velocity of the second frame with respect to the first. According to the formula above, if an object moving in a straight line with a constant speed in the first frame, i.e. a acceleration equals 0, then it does not move in a straight line with a constant speed in the second frame, i.e. acceleration nu is not 0. Hence, if the first frame is the inertial frame, then the second is not. Okay. A simple extension of the above argument allows us to conclude that any frame of reference which accelerates with respect to a given inertial frame is not itself an inertial frame. So, not inertial. Inertial. For most practical purposes, when studying the motions of objects close to Earth's surface, a reference frame which is fixed to respect to its surface is approximately inertial. However, if the trajectory of a projectile within such a frame is measured to high precision, then it will be found to deviate slightly from the predictions of Newtonian dynamics. See chapter 7. This deviation is due to the fact that the Earth is rotating and its surface is therefore accelerating towards its axis of rotation. When studying the Earth rotates, any body rotates, sorry. If you're here, that acceleration which you feel makes it not inertial frame. But we can assume that's not the case for the sake of calculations. Okay, when studying motions objects around reference frame is approximately inertial. However, if such orbits are measured to extremely high precision, then they will again be found to deviate slightly from the predictions of Newtonian mechanics. In this case, the deviation is due to the Earth's orbital motion around the Sun. When studying the orbits of planets in the solar system, a reference frame whose origin is the center of the Sun and whose coordinate axes are fixed with respect to distant stars is approximately inertial. In this case, any deviations of the orbits from the predictions of Newtonian dynamics due to the orbital motion of the Sun about the galactic center are far too small to be measurable. It should be noted that it is impossible to identify an absolute inertial frame. The best approximation to such a frame would be one in which cosmic microwave background appears to be approximately isotropic. Okay, so they suppose that the cosmic microwave background radiation, which is the CMB, which is basically the temperature of the universe, at some given point, which we will not assume is at 300,000 years after the Big Bang, because we will not assume a Big Bang here. We will come to the decision if the Big Bang is actually true later on. However, for a given dynamical problem, it is always possible to identify an approximate inertial frame. Furthermore, any deviations of such a frame from the true inertial frame can be incorporated into the framework of Newtonian dynamics via introduction of so-called fictitious forces. So, a simple fictitious force would be, what do you call it in English? You call it uh, uh, you you oof, um, you know, the fictitious forces. So a body is rotating, a fictitious force, and a fictitious force. Okay. Okay. Next. Okay. Newton's second law of motion. Newton's second law of motion. Newton's second law of motion essentially states that if a point object is subject to an external force F, then its equation of motion is given by dp dt equals F. So the change in the momentum is the force. Where the momentum P is the product of the object's inertial mass and velocity V. P equals mv. But we must be careful because sometimes P changes, sometimes m changes, sometimes V changes. If m is not a function of time, then the above expression to the familiar equation goes as m mv dt equals F, or F is equal to ma. But that is not the true form, or because m can also in rockets deviate by time because the rocket loses mass. Note that this equation only is valid for the in an inertial frame. Clearly, the inertial mass of the object measures its reluctance to deviate from its preferred state of uniform motion in a straight line. In an inertial frame, of course, the above equation of motion can only be solved if one have independent expression from the force. Okay, that makes sense. 1 second. I get it. Beautiful. Okay. An important corollary, corollary, corollary of Newton's second law is that force is a vector quantity. This must be the case, since this law equates force to the product of a scalar, mass, and a vector, acceleration. Note that the acceleration is obviously a vector because it is directly related to displacement, which is the prototype of all vectors. Okay. One consequence of force being a vector is that the two forces F1 and F2, both acting at a given point, have the same effect as a single force F equals F1 plus F2. Okay. Acting at the same point, where the summation is performed according to the laws of vector addition. Likewise, a single force acting at any given point has the exact same effect as two forces F1 and F2 acting at the same point, provided that, well, F1 plus F2 is equal to F. This method of combining and splitting forces is known as the resolution of forces and lies at the heart of many calculations in Newtonian dynamics. Taking the scalar product of equation 14 with velocity v, we obtain m v dv dt is equal to m 2 v squared dt. Okay, which is f times v. This can be written as dk over dt is equal to f times v, where k is equal to kinetic energy is equal to 1/2 mv squared. Okay. The right-hand side of the equation represents the rate at which the force does work on the object, i.e., the rate at which the force transfers energy to the object. The quantity k represents the energy of the object possesses by virtue of its motion. This type of energy is generally known as kinetic energy. Thus, equation 16 states that any work done on a point object by an external force goes to increase the object's kinetic energy. Suppose that under the action of the force F, our object from point P at time t to point Q at time t2, the net change of the object's kinetic energy is obtained by integrating the net from t1 to t2 f v dt, which is equal to p q f d r. Okay, perfect. since v is equal to dr dt, here dr is an element of the object, so boop, boop, boop. Next. As described in section A15, there are basically two kinds of forces in nature. Firstly, those those for which line integrals of type integral from P to Q f dr depend on the endpoints, but not on the path taken between these points. Okay. And secondly, those for which line integrals type integral from P to Q f dr depend both on the endpoints and the path taken between those points. The first kind of force is termed conservative, whereas the second is termed non-conservative. So we have conservative and non-C. It was also demonstrated in section A15 that if the line integral from P to Q of f dr is a path independent, then the force can always be written as the gradient of a scalar field, in other words, all conservative forces satisfy F is equal to the not nimda u, some scalar field. Note that, okay, P Q lambda dr is equal to the well, to this minus what did we call the second point? P, the first point. Irrespective of the path taken between P and Q, hence it follows from the equation 18 that delta K is equal to the negative of delta U. For conservative forces, another way of writing this is E is equal to kinetic plus potential, and is always a constant. Of course, we recognize this is an energy conservation equation. E is the object's total energy, which is conserved. K is the energy of the object that the object has by virtue of its motion, otherwise known as its kinetic energy. And U is the energy of the object which it has by virtue of its position, otherwise known as its potential energy. Note, however, that we only write such energy conservation equations for the conservative forces. Gravity is a good example of a conservative force. Non-conservative forces, on the other hand, do not conserve energy in general. This is because of some sort of frictional energy loss, which drains energy from the dynamical system whilst it remains in motion. Note that the potential energy is undefined to an arbitrary additive constant. In fact, it is only the difference in potential energy between the different points in space that is well defined. Okay, that's what we get there. And now off to the new. Why did I? Newton's third law of motion. Consider a system of n mutually interacting point objects. Let the eth object, whose mass is mi, be located at vector displacement r1, ri. Suppose that this object exerts a force F ji to the jth object. Likewise, suppose that the jth object exerts a force Fij to the ith object. Newton's third law of motion essentially states that these two forces are equal and opposite irrespective of their nature. In other words, Fij is equal to minus Fji. On the corollary of Newton's third law is that an object cannot exert a force on itself. Another corollary is that all forces in the universe have corresponding reactions. The only exceptions to this rule are the fictitious forces which arise in non-inertial reference frames, i.e. the centrifugal force, I wanted to say that, Coriolis force, which also I wanted to say, which appear in the rotating reference frames. Fictitious forces do not possess reactions. It should be noted that Newton's third law implies action at a distance. In other words, if the force that the object I exerts on an object J suddenly changes, then Newton's third law demands that there must be an immediate change in the force that object J exerts on an object I. Moreover, this must be true irrespective of distance between the two objects. However, we know that Einstein's theory of relativity forbids information from traveling through the universe faster than the velocity c, the speed of light, or the speed of causality. Okay, speed of causality mentioned. In a vacuum. Hence, action at a distance is also forbidden. In other words, if we force that the object I exerts that the object A suddenly changes, then there must be a time delay, which is at least long as it takes a light ray to propagate between the two objects, before the force that object J exerts on object I can respond. Of course, this means that Newton's third law is not, strictly speaking, correct. However, as long as we restrict our investigations to the motions of the dynamical systems on timescales that we long compared to the time required for that are long compared that are long like long compared to the time required for light rays to traverse these systems, Newton's third law can be regarded as approximately correct. In an inertial frame, Newton's second law of motion applied to the ith object yields mi derivative or second derivative of r1 ri dt squared is equal to the sum j equals 1 to j doesn't equal I f ij number of objects. Okay, note that the summation on the right hand side of the above equation excludes the case j equals I, since the ith object cannot exert a force on itself. Let us now take the above equation and sum it over all objects. We obtain the sum I equals 1 of n mi, the second derivative of ri, derivative of time squared, equals the sum Fij equals 1, number of objects, Fij, j equals, doesn't equal I, until then. Okay. Consider the sum of the forces on the right-hand side of the equation. Each element of this sum, Fij, say, can be paired with another element, Fji, in this case, which is equal and opposite according to the Newton's third law. In other words, the elements of the sum all cancel out in pairs. Thus, the net value of the sum is 0. It follows that the above equation can be written as the mass, the total mass of everything, the second derivative of r cm derivative of t squared is equal to 0, where m is the total mass, the quantity rcm is a vector displacement vector, the center of mass, center of mass, center of mass. Okay. Now, if we consider that the mass moves in a uniform straight line, then the center of mass velocity is this: dr center of mass dt is equal to the sum of I equals 1 to the n mi dri dt divided by the sum of I equals 1 to n mi. A comparison of equations 28 and 29 suggests that p is also constant. In other words, the total momentum of the system is conserved quantity, irrespective of the nature of the forces acting between the various components of the system. This result, which only holds if there is no net external force acting on the system, is a direct consequence of Newton's third law of motion. Taking the vector product equation with the position vector r, I, we obtain m I r I dot product r I dt squared is equal to the sum of j of 1 of n until j is not I. R1 dot f ij. However, it can be, where was I? However, it is easily seen that this goes, some math, which we will write, I guess, m I r I dot r d, the second derivative of r I with respect to dt squared is equal to d of the product, which we'll call product. The product divided by dt, which is di I dt, or I e is equal to mi ri dot dri dt. And it is the angular momentum of the ith particle about the origin of the coordinate system. The total angular momentum of the system about the origin takes the form of L, and it is I1 and I. So from I to the particles summed. Hence, summing the equation 30 over all particles dl over dt is equal to the sum of I and j equal 1 to n until I besides I equals j ri times fij. Consider the sum on the right hand side of the above equation. A general term ri dot product fij in this sum can always be paired with a matching term rj dot fji in which the indices have been swapped. Making use of the equation 23, the sum of the general matched pair can be written as ri dot fij plus rj dot fji, which is equal to ri minus rj times fij. Let us assume that the forces acting between the various components of the system are central in nature, so that Fij is parallel to Rij minus Rj. In other words, the force exerted on the object J by the object I either points directly forwards or directly away from the object I, or vice versa. This is a reasonable assumption, since most of the forces which we encounter in the world around us are of this type, example gravity. It follows that if the forces are central in nature, then the vector product of the right-hand side of the above expression is zero. We conclude that dl over dt is equal to 0. For all values of I and j, thus the sum of the right hand side of the equation is 0. For any kind of central force, we are left with that. In other words, the angular momentum of the system is conserved quantity, provided that the different components of the system interact via central forces and there is no net external torque acting. So we have angular momentum as velocity, and torque is above it. It's an acceleration of the rotating frame. Okay. Non-isolated systems. Up to now, we have only considered isolated dynamical systems, in which all of the forces acting on the system originate within the system itself. Let us now generalize our approach to deal with non-isolated dynamical systems, in which some of the forces originate outside the system. Consider a system of n mutually interacting point objects. Let mi and ri be the mass and the position of a vector of ith object, respectively. Suppose that the ith object is subject to the two forces. First, an internal force which originates from the other objects in the system, and the second, an external force which originates outside the system. In other words, let us consider acting let the force acting on the ith object take the form of Fi is equal to the sum of Ji n j to n f ij equals fi. Okay, where f Fij is the internal force exerted by the object J on the object I, and the Fi is the net external force acting on the object I. The equation of motion of the ith object thus is mi second derivative of ri d twice the derivative of time is equal to fi, which is equal to the to the to the sum of j equals 1 to n, where j and I cannot be the same. F Fij plus the sum of I equals 1 to the n Fi, which reduces to dp over dt is equal to F, which is F equals ma again. Okay, where F is equal to the I1 to n Fi. In the net external force acting on the object here, the sum over all internal forces is cancelled out in pairs due to Newton's third law. We conclude that the total system momentum evolves in a time according to the simple equation where there is a net external force acting on the system, but it is completely unaffected by the internal forces. To fact that equation 41 is similar in form to equation 13 suggests that the center of mass of the system of many point objects has analogous dynamics to point objects. Taking Ri dot equation 39 and summing over all objects, we obtain the torque. T equals the torque, where F is equal to the sum of I to 1 and Fi. Wait, I think I fucked it up. Yeah, I'm pretty sure I fucked it up. Wait, I lost concentration. It's bad. I need water as well. Yeah, that where where T or torque is equal to the sum of I to the 1 and Ri dot product Fi. Okay. Is the net external torque acting on the system. Here the sum over all internal torques is cancelled out in pairs, assuming that the internal forces are central in nature. We conclude that the total system angular momentum evolves in a time according to the simple equation 43, where there is a net external torque acting on the system, but is completely unaffected by the internal torques. Okay, because they go to zero. Exercises. Finally, I'm gonna go get some water. Getting water in 2 glasses. All right. Okay. Consider the isolated system of n-point objects interacting via gravity. Let the mass of and position vector of these ith object of m I and m be respectively. What is the vector equation of motion on the ith object? Write the expressions for total kinetic energy k and potential energy u of the system. Demonstrate from the equations of motion chi plus a is a conserved quantity. Okay. And do they have? Oh, they do not have. They do not have exercises. What if I go here? One-dimensional motion. Okay. Next. Previous. Okay. Consider a function of many variables f x1, x2, and so on. Such a function which satisfies f t x1 t x2 to txn is equal to t of t on a, which is a constant, a degree, homogeneous degree, I would assume, of f x1 to the xn for all t bigger than 0, all times larger than 0, and values of the x1 is termed a homogeneous function of a degree a. Prove the following theorem regarding homogeneous functions. Okay, we will not do everything here. I'm just using it to get back into it, and then we're going to do examples, like real examples. And that's going to be in an hour or so. Now we don't have much here to use, so we're going to go next. One-dimensional motion. What is up must come down. Multi-dimensional motion, planetary motion, two-body dynamics, rotating. So let us go through one-dimensional motion and multi-dimensional motion, and then we'll leave this for later. Okay. One-dimensional motion. Introduction. This chapter employs the Newton's laws to investigate one-dimensional motion. Particular attention is given to the various mathematical techniques commonly used to analyze oscillatory motion. Okay. Next. Okay. Consider a point particle of mass m moving in the x direction. Say, under the action of some x-directed force f of x. Suppose that f of x is a conservative force, example gravity. In this case, according to the equation 19, we can write f of x is equal to the minus potential energy of x dx. Okay. Where potential energy of x is the potential energy of the particle at position x. Let the curve take form showing the figure 2. Okay, that's the figure 2. Let's go. For instance, this curve might represent the gravitational potential energy of a cyclist freewheeling in a hilly region. Observe that we have set the potential energy at infinity to 0. which we are generally able to do. We are able to do that, since potential energy is undefined to an arbitrary additive constant. This is a fairly common convention. What can we deduce about the motion of the particle in this potential? Well, we knew about its total energy E, which is the sum of the kinetic energy and the potential energy in a constant of free motion, see equation 22. Hence, we can write K is equal K of X is equal to E minus U of X. However, we also know that the kinetic energy can never be negative, since K and neither m or v squared can be negative. Hence, the above expression tells us that the particle's motion is restricted to the region or regions in which the potential energy curve u of x falls below the value E. This idea is illustrated in figure 2. Suppose that the total energy of the system is E naught. It is clear from the figure that the particle is trapped inside one or the other of two dips in the potential in the potential. These dips are generally referred to as potential wells. Suppose that we now raise the energy to E1. In this case, the particle is free to enter or leave each potential well, but its motion is still bounded to some extent, since it clearly cannot move off to infinity. Finally, let us raise to the energy to E2. Now the particle is unbounded. It can move off to infinity. It is in conservative systems in which it makes sense to adopt the convention that the potential energy at infinity is zero. Bounded systems are characterized by E sub zero, whereas unbounded systems are characterized by E above zero. Okay. Okay. I understand. We can move on. The above discussion suggests that the motion of a particle moving in potential generally becomes less bounded as the total energy E of the system increases. Conversely, we would expect the motion of the to become more bounded as E decreases. In fact, if the energy becomes sufficiently small, then it appears likely that the system will settle down in an equilibrium state in which the particle is stationary. Let us try to identify any prospective equilibrium states. If the particle remains stationary, then it must be subject to the zero force, otherwise it will be accelerating. Hence, according to equation 45, an equilibrium state is characterized by du dx is equal to 0. In other words, an equilibrium state corresponds to either the maximum or the minimum potential energy curve. Ux, it can be seen that Ux curve shown in figure 2 has three associated equilibrium states located at x equals 0, x equals 1 here, and x equals 2 here. Let us now make a distinction between stable equilibrium points and unstable equilibrium points, where the particle is slightly displaced from a stable equilibrium point, then the resultant force F acting on it must always be such as to return to its point. In other words, if x equals x naught is an equilibrium point, then we require d of f x be less than 0. For stability, if the particle is displaced to the right so that x minus x naught is bigger than 0, then the force must act to the left so that F is smaller than 0 and vice versa. Likewise, if d of F dx x naught is bigger than 0. Then the equilibrium point x to x0 is unstable. It follows from the equation that stable equilibrium points are characterized by d squared u dx squared is bigger than 0. In other words, a stable equilibrium point corresponds to minimum of the potential energy curve u of x. Likewise, an unstable equilibrium point corresponds to the maximum of the ux curve. Hence, we conclude in figure 2, x is equal to x naught and x is equal to x 2 are stable equilibrium points, whereas x equals to x1 is an unstable equilibrium point. Of course, this makes perfect sense if we think of ux as a gravitational potential curve, so that u is directly proportional to height. In this case, all we are saying is that it's easy to confine a low energy mass at the bottom of a valley, but very difficult to balance the same mass on top of a hill, since any displacement of the mass will... now, note this finally if... okay. du dx is equal to d squared u dx squared is equal to 0. At any point or in any region, then we have what is known as a neutral equilibrium point. When we can move the particle slightly away from such a point and it will still remain in equilibrium, i.e. it will attempt to return to its initial state, nor it will continue to move. A neutral equilibrium point corresponds to a flat spot in an ux curve. Okay. Now we get to the fun stuff. The equation of motion of particles moving in one dimension under the action of a conservative force is in principle intangible, integrable, integrable, integrable. Oh my god! Since k is equal to a half mv squared, the energy conservation equation can be rearranged to give v is equals to plus minus the square root of 2e minus ux divided by m. Well, let's write respectively how v equals dx dt. This expression can be integrated to give. We integrate that and we just solve it with that, and where x t equals 0, x 0, x0 for sufficiently simple potential functions. Ux, the above equation can be solved to give x as the function of t. For instance, if u is equal to the normal u, no, it's not the normal u. If u is equal to chi x squared divided by 2, x0 is equal to 0, and the plus sign is chosen, then t is equal to m. The root of t is equal to the root of mk, the integral of 0 to k to e rooted, right, dy 1 plus y squared, which is equal to mk root sinus, because it's an integral, a negative sinus, or not a negative sinus, and an inverse sinus. Sorry, I'm rusty, very rusty. Of k 2e 1 half. That's a root x times x. Okay, which can be inverted to give x is equal to a sinus omega t. Okay, where a is equal to the 2e divided by k, and omega is equal to root of k divided by m. Note that the particle reverses direction each time it reaches one of the so-called turning points, x equals plus or minus a, at which u equals e, and so k is 0. Kinetic energy is 0, but u is equal to e. Okay. Next up. Velocity dependent forces. Velocity depth forces. We will be doing the exercises of the MIT platform and watching the MIT lectures as well. Probably. I don't know if they're copyrighted. I hope they're not. But yeah. One second. Alright. Okay. Consider a particle of mass m moving in one dimension under the action of a force F, which is a function of the particle's speed. V, but not of its displacement, x. Note that such force is not intrinsically non-conservative, since it clearly cannot be expressed as a minus the gradient of some potential function ux. Now, the particle's equation of motion is written m dv dt is equal to the f of v. Integrating this equation, we arrive at t over m. We swap. So we swap here. This goes there, and this goes there, and yeah, that's it. In principle, the above equation, since v is dx dt, integrating the equation, we can obtain x minus x naught over m, where x is a t0 is x 0. In this principle, the above equation can be solved to give v of x. Let us now consider a specific example. Suppose that an object of mass m falls vertically under gravity. Let's draw that. here. Let us falls under gravity. Vertically, horizontal, vertically. Falls under gravity. So we have an F. This is a time equals 0. Now is assumed to be at rest, which follows that x v is also 0. Suppose that in the additional force of gravity mg, where the g is the gravitational acceleration, which we will take as just that, our object is subject to a retarding air resistance force which is proportional to the square of its instantaneous velocity. The object's equation of motion is thus. So we have uh, m mdv dt is equal to mg minus something, and that minus something is a constant which we cannot say k. C v squared. Okay, they decided upon v squared. So square of its instantaneous velocity. It did say that. I could have assumed. C is bigger than 0, so C is bigger than 0. This equation can be integrated to give this. Let's integrate it. Let's integrate it. To V dv v v minus v v divided by vt squared is equal to gt, because we can always get this on the other side, and we can get this on this side. Okay, okay. Making a change of variable we obtain. Okay, he did some changes of variables, which is, you know, to v. He just did vt. We obtain dy divided by 1 minus y squared is equal to g vt vt times t. Okay, because v is equal to mg divided by c, root of that. Okay. The left hand side of the above equation is now a standard integral, which can be solved as tan h minus 1 v vt gt vt, and so v is equal to vt tan h gt divided by vt. Okay. Oof. Oh. Thus, when t is smaller than vt, vt divided by g, we obtain the standard v is gt, since tan x to the x 4x smaller than 1 higher than when t is bigger, a lot bigger than vt divided by g. We get v is approximately vt, since tan x approximately 1 for x bigger than 1. It follows that air resistance prevents the downward velocity of an object from increasing indefinitely as it falls, which is expected. Instead, at large times, the velocity asymptotically approaches the so-called terminal velocity, so Vt, at which the gravitational and air resistance forces balance. The equation of motion of our falling object is also written as m v dv of dx is equal to mg minus t v squared. Okay, this can be integrated. Again, this is the same integration and the change of variables. So we'll just skip a step and we'll say 0 to v vt squared dy 1 minus y is equal to x by the xt, where xt m divided by 2c. Okay. Then the left hand side of the above equation is now a standard integral, which can be solved to give a logarithm, a negative logarithm of 1 minus v vt squared equals x xt. Or we can simplify vt 1 minus e1 minus e to the power of minus x xt, and all of that is to the root. It follows that our object needs to fall a distance of order xt before it achieves its terminal velocity. Incidentally, it is quite easy to account for air resistance force, which scales as the square of the projectile's velocity. Let us imagine that a projectile is moving sufficiently rapidly that air does not have enough time to flow around it, and instead gets knocked out of the way. If our projectile has a cross-sectional area A perpendicular to the direction of motion, and it's moving with a speed v, then the mass of the air that it knocks out of its way per second is some density a v, where a is the mass density of the air. Suppose that the air knocked out of the way is being pushed out in the direction of the projectile's motion with a speed of order v. Okay. It follows that the air gains of momentum per unit time. Okay. In the direction of the projectile's motion. Hence, the Newton's law, the projectile loses the same momentum per unit time in the direction of motion. In the other projectiles is subject to the drag force magnitude, F drag, of c. How do I write that shit? Rho a v squared, acting in the opposite direction to its motion. Hence, c is an O1 dimensionless constant known as the drag coefficient, which depends on the exact shape of the projectile. Obviously, streamlined objects such as arrows have a small drag coefficients, whereas non-streamlined objects such as bricks have large drag coefficients. From before the terminal velocity over projectiles Vt, m, g, c root of where m is its mass and c is equal to cp of a, writing m a dp, where d is the typical linear dimension of the projectile and rho its mass density. We obtain the final formula Vt is equal to rho times g dimensionless constant, rho air times c, and all that rooted. The above expression tells us that large, dense, streamlined objects, medicine balls, tend to have large terminal velocities, and small, rarefied, non-streamlined projectiles, example feathers, tend to have small terminal velocities. Hence, the former type of projectile is relatively less affected by air resistance than the latter. Okay, next. Simple harmonic motion, baby. Okay. I'm smoking because I want to try. Uh, I want to try something better. Okay. Consider the motion of a point particle m, which is slightly displaced from a stable equilibrium at point x equals 0. Suppose that the particle is moving in a conservative force field, okay, Fx. According to the analysis of section 3.2, in order for x to equal 0 to be stable equilibrium point, we require both that f at 0 is equal to 0 and that d of f at 0, or a displacement of x, is smaller than 0. Now our particle obeys Newton's second law of motion. M d squared x divided by dt squared is equal to f of x. Let us assume that it is always stays fairly close to the equilibrium point. In this case, to a good approximation, we can represent f of x via truncated Taylor expansion about this point. In other words, okay, a truncated Taylor expansion. I should really get a better one. Better. Because this is not gonna be, you need a lot of pre-knowledge for this. I'm not gonna be able to keep up with quantum mechanics. Like this. Okay, doesn't matter. However, according to 72 and 73, the expression written is f of x approximately is minus tau or pi? Tau or pi? Omega naught squared x, where d of f 0 divided by d of x is equal to minus m. That's m. Mass. You stupid idiot. Okay. Okay. Provided no large. Good. Good. X. Wait. ds2 plus x is 0. Equation is called a simple harmonic oscillator, and the solution is well known, and it is x of t is equal to a sinus omega 0t minus phi constant. The pattern of motion described by above expression, which is called a simple harmonic velocity, is periodic in time with a repetition period of t equals 2 pi omega naught, and oscillates between x plus and minus a. Here a is called the amplitude of the motion, where parameter f of f0, known as the phase angle, simply shifts the pattern of motion forwards and backwards in time. Figure shows some examples of simple harmonic motions. Plus pi 4, minus pi 4 correspond to the solid, short dashed, and long dashed curves respectively. Note that the frequency omega naught and hence the period t0 of simple harmonic motion is determined by the parameters appearing in the simple harmonic equation. However, the amplitude a and the phase angle f0 are the two integration constants of this second order ordinary differential equation, and thus determined by the initial conditions, by the particle's initial displacement and velocity. Okay. Now from the equations 45 and 76, the potential energy of our particle is at the position x is approximately u of x is equal to 1/2 mass times the angular squared x squared. Hence, the total energy written is that, and we will write it as E is equal the kinetic plus the potential. The potential. The kinetic is 1/2 m dx dt squared, and this is the 1/2 m omega naught squared x squared, giving this. Where use has been made of this, note that constant time. Yeah, okay, that's enough from that one. Let me see up. Okay, when we finish this 1, 2, 3, 4, 5, 6, we go to MIT. Because if I go up, we have done this, and that's not a lot. We should probably do multidimensional motion as well. Electric and magnetic fields, we will do that again. Rotating reference frames, rigid body rotation, long-ranging dynamics, Hamiltonian dynamics, coupled theory, three-body problem, lunar motion, the chaotic potential, vector algebra, and vector calculus. Okay, let me first see something else. We go back. We've covered a lot. Newtonian dynamics professor, thank you. Okay. We go to MIT Open Courseware. And we go physics. And we see physics from undergraduate. I want relevance How would I classical mechanics? I guess classical. Physics 1, classical mechanics. Okay. Electricity and magnetism. 401. This is 401. Let's see if this is good. Exams with solutions. Let's go to YouTube. YouTube. MIT Core the open course physics. Quantum physics. This is quantum. This we need. 800. I'm just gonna go 800. 1. Classical mechanics. No. Which ones should I follow? Let me see exams. If that's knowledge the course. Download the course. Oh, wait, it is downloaded. We got this video.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of
Videos. Okay. And has it downloaded? Done. Alright. Pages, resources. God damn it, I have to. Let's see. Download. What is this? Okay, is that pages, assignments. So you just go here, I guess. I don't need this. Delete. Thank you. Exams. Lecture notes. Okay. Lecture 1. Let us see. Lecture 1. And we are going to go MIT. Fuck. Let me see what's here. Resources. Okay. Exams. Final exam. How do I get this a bit bigger? I don't want to download it. Okay. Pokey. Let me see the final exam. If I could actually do it right now. Summary of equations. Newton's first law. Okay, that's point mass done by force. That's easy. Okay. Okay. What about electrons? PRS sold. What? Lecture notes. Lecture 2. This does not have everything, I see. Assignments also do not have everything. It's an introductory. Well, what should we be looking for? L under classical mechanics. Maybe it's this one or this one. Undergraduate, 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 undergraduate. With an experimental focus. I don't care about the experimental focus. Let me see exams and socials now. Syllabus. Okay, okay. Oh, I missed the whole tab. Jesus Christ. We have 2 more hours. Is the advanced physics 0 is the advanced version of the first year classical mechanics. But faster pace and slightly more depth. That's what we want. Right. Calendar. Okay. Readings. From the textbook. That is the textbook. Problem set. Exams. Projects. Related resources. Calendar. Readings. Let me see if I can find this. Okay. An introduction to mechanics. Better. That's better. Preface. Okay. Factors and kinematics. Definition of a vector. I mean, we can go this way. But let us go. Where's this way? On times 2. On times 2. Because, oh god, I'm not listening this to... Okay, and this is... Let me calculate it. 30, 45, 50, 50. Around 40 videos, 10 of which are not. So 10 minus 50 equals minus 40. 40 times 50 divided by 2. 20 times 50. 0, 0, 1. 1 hours. Minutes. Minutes. Divided by 60. Boop, boop. 6 divided by 100 is 1. 40. 40. 40 is 36. So 6. 6, 6, 6, 6. That's many hours. Okay. 16 hours. I guess we're watching that for the next 6 hours. But also supplementing it with this one. If it's a good book. Let's see if it's a good book. Only from central motion. How many pages? Around 500 pages. 500 times 5 minutes. 1000 minutes. So around 30 hours. Meaning I'll spend a great deal. And then examples 20, that's 50 hours. If I spend 4 hours a day, I need to increase it a bit more. Because this will gonna take well, it's gonna take oh, it's gonna take 20 and 20 and 8. 20 is 5. 12.5. Not many days for mechanics alone. Okay. But now I know a bit more of the exercises and the book. We will be reading the book and the exercises together. So, yeah. Time to. Now, which one do I want? 1 second, 1 second. This is strawberry. Do I want strawberry? I guess I do want strawberry because my other fell somewhere. And I wanted to try it really bad. Is it there? Is it there? 1 second. Okay, I got my meds. And it's time to put strawberry inside of my vape. That's 2 more hours. I could have sworn I put it somewhere. The mental, but guess we're not doing mental. Oh, beautiful. Okay. Time to drink my meds and it's a break. We're gonna watch videos. Okay. That. And we got that. Okay, we're back. Let me see if it's working. If it's working. Let me see if it's working. Is it working? That. Good. Good. So, what we found is this is useless. This is useless. This is useless. This is useless. Useless. This is potentially useful. This is what we'll be using. This is also what we'll be using. This is the exam we're gonna pass eventually. And so on. So 50 hours to learn classical mechanics. Doesn't sound insane. But I might need to, you know, do, if it's 50 hours for a subject, 50 hours for a subject. And let me find the subjects I want. Lots of them. Let's go to OpenCourseware and see the subjects which need to be done. So we're following Physics 1 Classical Mechanics. This one. 8.012. Okay. Just flip physics undergraduate. Or I should Google that. MIT physics and math major undergraduate subjects. Yeah. Subjects. Fall. Okay. Okay. So we're doing this one. Then we decide on one of these three. Let me see this one. Let me move the camera around. Okay. Undergraduate subjects. Next one. That's what we're doing. Physics 2. Okay, then 8.022, then 8 resonance, 8.03, 8.033, 8.04, 8.044, 8.05, 8.06, 8.07, 8.08, 8.09. Elective subjects. So this is for physics first. I should write it a bit more formally. 8.012, 8.022, 8.03, 8.033, 8.04, 8.044, 44, 5, 6, 7, 8, 9, 8.05, 0.06, 7, 8, and 8.09. Okay. Now, besides that, we're doing 8.20, 8.21, 8.223, 8.224, 8.225, damn, that's a lot. It still keeps going. Okay. Relativity to 8.228, 8.231, biological physics we do want to do. I'm interested in it. 241. And we can check and mark them later. You know, to know your enemy, you must know your enemy. So I will do 8. I will put a red dot. 8.251 later. Okay. Nuclear and particle physics. 8.276, 8.277, 8.284. The early universe, I am very much in wanting to understand the early universe. 8.6. Just so we know when I'm completing all this shit. What does the J mean? Fluid physics. 8.292. That's useless. Selected physics teaching. Okay. I don't know these other ones. Okay. That's for physics. So 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19, 20, 21, 22, 24. That's for physics. Okay. EIP. What's the difference? I selected fall. That's fall. It doesn't go with. Okay. Okay. I did do that. Experimental data science and physics. Physics of energy. I do have 21. I think I do have 21. I do have 21. Fluid, I do have. Classical mechanics. 309. 8. 309. That's 25. Electromagnetic theory. 311. 26. Quantum theory 2. Relativistic quantum fields theory. I do want to know that. 8. 3, 2, 2. That's 27. 22. Quantum theory, relativistic. 2. Relativistic quantum fields theory. Louis. 8. 3, 2, 3. 28. 8. 3, 2, 5. 29. 8. 3, 4, 4. That's 30. Atomic and optical physics. Non-linear optics. 8.421. 31. 8.431. 32. Now I'm gonna create a document by which we will go. Nonlinear optics. 8.512. 33. 8.51 4 34 8.614 35 8.711 8.871 8.901 8.9062 and that's it. That's 36, 37, 38, and 39. This will be interesting. And to add the 40th one is gonna be 8.29, right? 0. That's 40. Okay. And we go with it with this. Now that's the Department of Physics. MIT Math Department lectures open courseware. This is physics, which is 50 hours times 40, which is 2000. 2000 hours. That's a lot of hours for just physics. For just physics. But physics is about math as well. And I have to add a lot of them. Undergraduate. A lot of undergraduate maths ones. So let's go with math now. Math. $18.01. 18.02. 18.022. 18. 0.024, 18.3, 18.034, 18 point. I'm assuming all of these have books. So now I'm planning stage. I was revisiting physics and now I'm in the planning stage. 18.004, 18.05, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. 0.05, 18.06, 18.062, 18.100, C, 18.101, 18.102, My journey will not stop with this. This is just like a base knowledge, undergraduate knowledge. Then we move to graduate knowledge, and then we move to reading old papers and trying to understand them. Where were we? Point analysis, complex reverse, summary analysis. 12, 18 point. Geometry and quantum field theory. 18.15 should do. 18.5 should do. Chaos. 18.353. It's chaos. 18.400. Free, pardon. 9, 10, 11, 12, 13, 14, 15, 16, 17. Uh, 18.410, 18 point 433, 18 point 433. I already said 433. 40, 40. Oh no, I didn't. 40.443. 18.70, 18.701, 18.702, 18.703, 18.781, 18.782, 18 point topology 1, 18 point 950, 18 point 18. And I will not plan afterwards the graduate things because I could, but no, I should. My specialization, I guess. Differential geometry. 9. What the fuck? The art of counting. Introduction to MATLAB. Does nothing good has ever come out of that. Okay, that's okay. 18, 19, 20, 21, 22, 25, 26, 27, 28, 29. And I could put a 30th there just for fun and giggles, and that's... Did I put 409? I did not. 18.409. 30. That's math. That's math. That's 50 hours times 30. 150 hours. Okay. Now we have how much? 2000 in physics and 1000. We have 350 hours. Okay. Current stream. Current is 5 4 hours daily. That's too little. Because with 4 hours daily, my calculator will help me with this one. Because I'm a physicist. 4. It will take me 875 days. If I cut that in half, if I move this to 6 hours daily, that's 300 divided by 6 hours. That's 583 days. We want it even less. We want to be able to, next year, know so much that it's insane. So we will go to 8 hours a day. 2 streams, 4 hours. Divided by 8. 437 days. To really know it. To really know it. Now let me just my initial calculation. 50 hours per subject. Is that an... Let's see. Like how much time per subject per term? You do. Okay. Not helpful, Quora, as always. Instructional units. How much time to learn classical mechanics? How much time? Give me a time. ChatGPT. ChatGPT. Okay, so I've picked my undergraduate classes in MIT, which learn it's 40 plus 40 was 70 classes. How long do you think will it take me in hours to truly master one on average? I need that info really bad. And ChatGPT knows. Per course, 200 hours. That does not seem nice. That does not seem nice. Let me open the book. The book. Where is the book? Is this the book? It's the book. Okay. Time myself on this page. It's 3 minutes per page. Average book, probably 300 pages. Probably 300 pages. So calculator, 300 pages times 3 minutes per page. That's 90 minutes divided by 60. To read the book, it will take me 15 hours. So I will scrap all this. No, I don't want that. I'm sorry. And this one should be deleted. Okay. Okay, so we have 70 subjects. 300 pages. 3 minutes per page. To read the book, not to understand. That is 15 hours. Okay, on top of that, 15 hours for examples. That's 30 hours. 30 hours times 70 subjects. Subjects. 70 times 30. 200 hours. Okay. this seems like a more realistic number. So if I go down to this god awful page, okay, that's 2,000 hours. I will consider option 1, 4, 6, and 8 hours a day. $2,000 hours divided by 24. No, we're not doing 24. We're doing 500 hours. 300 hours. 200 hours. For all of them. 200 days. Sorry. Days. 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 Okay. So, I could master it all this year. With 2 4-hour streams per day. Okay. So this is gonna be the truth. So I must do 200 hours, pardon, days of 4 times 2-hour sessions. 4 undergraduate. Okay. I'm a genius. I can do it. Stupid idiot. Okay. Now let us pose a question. And the question is, how many graduate are there? Which I would like to attend. This is for math. Let's start with the math. Graduate math. These are harder. So I'll be giving him 40 hours per subject. but there are less of them, much less of them. So, and much less I would actually want them. So let's go. Graduate, advanced calculus, computer science, engineering, mathematical methods, no, college, no. Several complex variables. 18.117. 18.125. 18.155. 18.156. 18.175. 18.177. 18.305. 18.306. 18.307. 18.315. There's a lot. There's a lot. I could do it something like this. Okay. No. No, 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 no. Okay. No, no, no. No, no, no. 'Cause So it's basically all of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 27, 28, 29, 30, 33, 34, 50. 30 hours. 50. Graduate physics. All subjects. Undergraduate subjects. Okay, let's go. Elective subjects. Graduate subjects. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20. It's 50. It's 50 again. Yeah, it's 50. Okay. 50. 30 hours. That is, my friends, 3,000 hours again, which will take me 4 times 2. Calculator. 300 divided by 8. 375 days. That's how much it will take. So, undergraduate 8 hours a day, we said 200 days. Graduate 8 hours a day, 400 days. Okay. Then papers. Scientifically important papers in a field. And papers. ChatGPT will help here. Okay. So how many relevant math and physics old papers are there? I am the ones which detective phenomena. That's very important ones. Let me see how many papers there are. Short as the paper is 60 pages. How many papers? Eight hours a day. So let me see. Say 1,000 papers. Or tens. Thousand. What is the average size of paper? 20 pages. If they're harder, it will take me 5 minutes per page. Meaning, meaning 20 pages per paper, it's gonna be 100 minutes. Okay, we can be good boys and we're gonna say 2 hours. That's 2000 hours of 8 day. That's 200 days. So the plan, 200 days undergraduate, 400 days graduate, 200 days papers, 800 days total. Calculator, divided by 356, a bit more than 2 years. Three-year plan. Year 1, under, year 1, graduate, year 2, graduate, year 3, papers. 3-year plan 2. Greatness. Today is the first day, which was just planning. So the 23rd of January 2025. 16th of February 2028. 5th of December 2027. That's it. That's what I want. I found my subjects. I found everything. And okay, plan. Day. 11. $11, $12, $13. 02. Okay. So 4 hours. Art. YouTube. Game. X. Redacted. Methodism. Equals downs. 4 hours. Okay. I'm satisfied. Necessity. Necess. That's these 4 hours, which are swappable, maybe. Of a week. would mean 4 plus 2 plus 2, 8, 12. Monday, 12 hours. Thursday, 12. Wednesday, 16 hours. Tuesday. 14 hours. Friday, 12 hours. Saturday, clear this document valid. That's it, folks. That's it. I'm gonna end the stream. Let me save this. Physics Day 1 is saved. We can put the journal somewhere. What is it called? Oh. A necessity. A necessity. A necessity is a necessity. Goodbye. Hope I make a good video. Anyhow, I want to announce now my insane plan, and let me rot.